You are currently plummeting through a hole in space, 2 billion light-years wide. Scientists proved this in 2013, and most people still don't know. We reside in the KBC void, a cosmic desert in which stuff is 20% thinner than it should be. This void distorts our perception of reality itself. The universe seems to expand quicker here than anywhere else. We will explore the revelation that broke cosmology by breaking down our most fundamental equations, investigate why 90% of space is emptiness, and learn what it means to reside on the cosmic edges. If you're ready to perceive the cosmos differently, click the like button and subscribe. Prepare yourselves. We begin. 3 astronomers were counting galaxies when they discovered something unbelievable. Ryan Keenan, Amy Barger, and Lennox Cowie studied 35,000 galaxies in 2013, charting their positions across billions of light-years. The figures were incorrect. Everywhere they examined near Earth, there were less galaxies than there should have been, by 20%. The pattern spread outward in all directions for a billion light-years, producing a sphere of cosmic emptiness, with us near the center. This was not a tiny distance between galaxy clusters. According to mainstream cosmology, there should not have been a void on this scale. The researchers triple-check their data, conduct several galaxy surveys, and investigate the sky from various perspectives. The results remained consistent. Our galaxy and everything in it exist within a thick bubble of space, so massive. It dwarfs everything else we've ever seen. The discovery was given a seemingly casual moniker, the KBC Void, after the initials of its 3 discoverers, yet there is nothing casual about what it signifies in the standard model of cosmology. When you zoom out far enough, the universe should appear about uniform. Sure, galaxies cluster together and leave empty areas between them, as is to be expected, but imagine a region this large with such a substantial matter deficiency. That tests the limits of what random chance can explain in computer simulations of how the universe formed from the Big Bang, which rarely produce holes this huge and empty when they do. It requires extremely uncommon initial conditions. The statistical likelihood is less than 1 out of 1,000. Some scientists determined that it would require a 10 sigma divergence from average density, implying that it is so uncommon that one would not exist in the entire observable universe. Yet here we are, living within one. If we live in such an exceptional area, the repercussions begin to cascade immediately. Does this distort every measurement we make when we point our telescopes toward distant supernova to see how fast the universe is expanding? Are we experiencing the genuine cosmic expansion rate, or a skewed local version? For years, the void hypothesis provided an explanation for one of modern cosmology's most perplexing puzzles, the Hubble tension. Scientists have measured 2 distinct expansion rates, depending on whether they are looking at the old cosmos or the nearby universe. The statistics differ by 9%, which may sound minor, but constitutes a problem. Both metrics are extremely exact. Both should provide the same answer. They do not if Earth is inside a vast under-dense region with gravity from heavier matter encircling the void. Would tug outward on galaxies within it, giving them more velocity as they moved away from us, making the local expansion appear faster than normal. Suddenly, the contradicting measurements made sense. We're not measuring the universe incorrectly. We're measuring it from within a hole. This insight altered everything, but it also created an unsettling conundrum that cosmologists are still wrestling with. If our location is so odd, can we trust what we think we know about the universe? What happens next illustrates how odd our cosmic neighborhood truly is. Cosmic voids are not entirely empty, making them much odd than their name implies. Between these lonely galaxies, there exist expanses of space filled with mostly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity scarcely works without enough mass to hold things together. No new galaxy can develop without first forming its structure. Clusters can form, but no rich superclusters emerge. The vacuum remains void. This void has far-reaching repercussions for physics itself. Gravity is already the weakest fundamental force in nature, requiring large masses. Gravity, like planets and stars, has less of an influence in a vacuum where material is limited. The dominant force becomes dark energy, the unknown pressure that accelerates cosmic expansion in densely packed galaxies. Gravity fights against dark energy, inhibiting its proliferation in those locations. Inside voids, gravity loses its tug of battle. Dark energy prevails decisively. As a result, voids expand more rapidly than the rest of the cosmos. They expand like bubbles, pushing their limits outward, while the filaments of galaxies surrounding them serve as walls. This generates a self-reinforcing cycle. As a vacuum expands, it becomes emptier, allowing for even quicker expansion. Scientists have confirmed this through thorough observation. They measured how galaxies near void borders move in comparison to galaxies in denser regions. The void galaxies are accelerating away from the center, faster than cosmic expansion alone could explain, implying that something is pushing them outward. That something is the gravitational attraction of all matter beyond the emptiness. Imagine a blank as a valley surrounded by mountains. Gravity pulls down from the mountains into the valley. But, since we're dealing about space rather than topography, that pull causes galaxies to fall outward rather than inward. The effect is measurable and significant. Our galaxy is traveling away from the local emptiness at a rate of 600,000 Faka. Driven by this gravitational imbalance, the interior of a void becomes an unusual environment for physics. Light passes through it, with less gravitational influence than light going through ordinary space. This has modest effects on observations. Astronomers studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, observe that light passing through voids seems somewhat cooler. The lesser gravity in voids results in less gravitational redshift, which appears as chilly patches on temperature maps of the early cosmos. These chilly locations coincide precisely with where we see enormous holes today. This alignment is not coincidental. It's physics. Understanding how voids become empty helps to explain why they are so important in cosmology. They aren't merely uninteresting gaps between intriguing galaxy clusters. They are laboratories where dark energy reigns supreme and gravity takes a back seat, while researchers investigate how matter behaves differently in voids versus dense places. Scientists debate fundamental hypotheses about how the cosmos works. The KBC emptiness around us may be disturbing because it challenges our cosmic norms, but it also provides a unique opportunity. We are in an ideal position to examine the universe's most extreme low-density settings, as well as the structure that houses these voids. It's far stranger than anyone expected. The universe isn't a smooth soup of evenly spaced galaxies. Instead, it resembles Swiss cheese, with thick stuff forming walls and filaments around massive hollow voids. This foam-like architecture is known as the cosmic web, and it is the greatest structure in. Galaxy clusters form where numerous filaments connect, resulting in nodes of high matter density. These nodes sparkle brilliantly, with millions of galaxies clustered close together. Filaments stretch between them, connecting galaxy clusters that can span hundreds of millions of light years. These filaments form walls and enormous sheets. Galaxies cluster at higher than average concentrations between filaments and walls, with voids taking up the majority of the volume, but having little mass. The structure was not always clear. Astronomers spent decades photographing the sky and counting galaxies, but the full three-dimensional structure remained concealed. The distance measurements were inadequate. Galaxies that appeared to be near to each other could in fact be separated by billions of light years, with one far further away than the other. The cosmic web emerged only when astronomers began measuring galaxy redshifts consistently in the 1970s and 1980s. Redshift surveys enabled astronomers to determine how far away each galaxy was, by determining how far the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution came into sight. The universe had structure at scales that no one predicted. The first major vacuum was discovered in 1978 by two independent teams who detected vast under-dense zones. More surveys followed. Each map delves further into space, exposing a more complicated web. The Sloan Digital Sky Survey, which began in 2000, produced amazing three-dimensional maps that span billions of light years. These maps depict the cosmic web in breathtaking detail, with filaments that twist and branch like blood veins, and holes appearing as dark bubbles. The largest structures, which can span 500 million light-years, include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. On the other end of the spectrum, supervoids like the Radius Void stretch 1.8 billion light-years wide, with fewer galaxies than the KBC void combined. These characteristics suggest that the universe is organized on considerably larger sizes than anyone could have expected. Galaxies aren't the essential building blocks. The web is the structure, with galaxies denoting where matter concentrates. Why is the universe organized this way? The solution can be traced back to the Big Bang, when matter was not totally uniform. Quantum fluctuations during the universe's first fraction of a second resulted in minute differences in density. Some locations are slightly denser than the average, while others are significantly less dense. These differences were minuscule, perhaps 1 part in 100,000, but gravity magnifies even minor advantages. Denser locations attracted more matter, making them denser. Even less crowded places lost matter to their surroundings. Over hundreds of millions of years, the planet has become increasingly depleted. This procedure accelerated. Small clumps formed into larger clumps, which then merged into galactic clusters, which aligned to form filaments. Meanwhile, the thick sections below grew into voids. The cosmic web is essentially gravity at work over cosmic time, transforming barely perceptible starting ripples into the most magnificent building in existence today. Voids account for approximately 90% of total space. Filaments and clusters account for the remaining 10%, but comprise the majority of the bulk. This imbalance determines the universe's character. We live in a cosmos punctured by emptiness rather than one packed with galaxies. By the occasional concentration of matter. The KBC vacuum is only one bubble in this environment, but it happens to be our bubble, which has a significant impact on what we observe and how we understand reality. The following chapter indicates exactly where we lie within this vast hole. The Milky Way isn't in the center of the KBC emptiness, but it's close enough to matter. Measurements place our galaxy between 200 and 400 million light-years from the void's real core. That may seem like a long distance, and it is when compared to what humans have experienced, but the nothingness extends outward for 1 billion light-years in every direction from its core. Our offset is relatively minimal. We are well placed in the underdense region, surrounded by voids and a low-density environment in all directions. This is not a random spot. It has implications for every observation and conclusion we reach about cosmology. If we were fully outside the void in one of the dense filaments, our measurements of the universe's expansion would be very different. We would calculate a slower rate of expansion, and the Hubble tension would not exist. Our greater cosmic surroundings provides another dimension to this story. The Milky Way is part of the local group, which includes our massive neighbor Andromeda and approximately 80 other galaxies. The local group is located within the Laia-Key supercluster, a large cluster of around 100,000 galaxies scattered over 520 million light-years. Laniakea is immense by any normal standard, but even this supercluster exists within the KBC abyss. Think about that for a moment. A structure containing 100,000 galaxies is still considered part of an underdense region. The emptiness is so massive that it can swallow entire superclusters and still have room to spare. Laniakea is part of the limited population of matter spread throughout the emptiness, one of the few concentrations in an otherwise barren landscape. The local group is also influenced by another adjacent void, known as the local void, which is separate from but linked to the bigger KBC void. The local emptiness, which reaches for around 200 million light-years, is next to our position. Our galaxy is moving away from it. At 600,000 miles per hour, propelled by the gravitational attraction of denser places, its motion is distinct from the broader cosmic expansion. It is a peculiar velocity, which means it is caused by local gravitational effects rather than the stretching of space itself. These unusual velocities confound efforts to determine the true expansion rate because they add extra motion to the expansion signal. Astronomers must carefully account for these local effects, but in a supervoid, they are amplified and more difficult to separate cleanly. The gap's influence extends far further. When scientists study the motion of galaxies at distances of 250 million light-years, they discover bulk flows that exceed traditional cosmology expectations. Entire portions of space are traveling quicker than they should be, flowing in coherent patterns caused by gaps and gravitational imbalance. The KBC vacuum generates a large-scale velocity field, which impacts everything inside it. Galaxies do not simply sit in an empty space, silently expanding with the cosmos. They are actively responding to the gravitational environment, accelerating outward from the underdensity to denser structures beyond the void's border. This makes our particular region of the universe more dynamic and unusual than the tranquil uniform cosmos that traditional models predict. Our position within the emptiness also influences how we observe light from distant galaxies, travels through space on its way to our telescopes. That light has less gravitational interaction than light. Traveling through denser zones, the reduced gravity has modest effects on light, wavelength, and energy. Furthermore, the void alters the dispersion of materials we observe. When we look outward from within the void, we may see a shell of denser materials encircling us in every direction. That shell appears as a concentration of galaxy clusters and filaments at a given distance. Beyond the shell, the cosmos returns to its normal density. This generates an observational bias. We are not selecting a random position in the cosmos. We're sampling from within one of its most severe characteristics. Living in the vacuum entails dealing with systematic uncertainty about how typical our measurements are. Every measurement you've ever heard about the universe's expansion rate could be incorrect, not because scientists committed errors, but because we're measuring from inside a cosmic hole, which distorts the signal. The issue arises when astronomers employ several ways to determine the Hubble constant, which informs us how quickly space expands. One method examines the cosmic microwave background ancient light from when the cosmos was only 380,000 years old. This light encodes information about the early universe's density and rate of expansion. Scientists enter this data into cosmological models to determine what the expansion rate should be now. The answer is around 67 kilometers per second per megaparsec. That indicates that for every megaparsec of distance, approximately 3.3 million light-years, space expands at 67 kilometers per second. The second strategy looks for nearby objects of known brightness, specifically type Ia supernova, Cepheid variable stars. These objects serve as cosmic measuring sticks, as astronomers can determine how bright they should be by comparing their real brightness to their apparent brightness. Scientists calculate their distance in relation to Earth. Combining distance and redshift measurements yields the expansion rate directly. This local technique regularly yields a higher value, approximately 73 kilometers per second per megaparsec. The difference is 9%. Both measures are quite accurate, with very small error margins. Both should yield the same response if cosmology is true, but they don't. This disparity is known as the Hubble tension, and it has reached 5 sigma statistical significance, which means there is less than a 1 in a million probability. It's merely random variation. The KBC void explains why these figures differ. When we estimate the expansion rate of a nearby supernova, we are measuring within the void. The vacuum's low density means that less gravity is pressing back on the expanding matter from denser locations outside the void. Gravity draws galaxies within it, increasing outward velocity. Galaxies appear to recede more rapidly than they would in a typical location. This increases the local Hubble constant measurement. We are not measuring the universe's actual expansion rate. We are measuring both the expansion rate and the void's unusual velocity field. When scientists model how a void of the KC's size and depth would affect local measurement, the effect is strong enough to account for the majority, if not all, of the measured stress. They discovered that it may increase the apparent expansion rate by the exact amount required to match measurements. But this is when things get uncomfortable. If the emptiness explains our local measurements, those measurements may be systematically distorted by our position. Some scientists argue that this result violates the cosmological principle, which holds that Earth exists, does not have a special place. The principle states that the universe should appear nearly the same from whatever perspective. When you average over big enough scales, finding yourself inside a gigantic vacuum with major effects on our measurements appears to contradict that assumption. It implies that we are in an unusual environment, which makes physicists uncomfortable. Science has gradually decentered mankind from its unique cosmic locations. Earth is not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy isn't the center of anything. And now we're meant to believe. We just happen to live in one of the largest holes ever seen. Many scholars are concerned about statistical improbability, but evidence continues to build. The emptiness exists. Our measurements are inconsistent. The void's effects match the observations. Whether we like the consequences or not, the cosmos may be lying to us about its expanding pace, or, more precisely, our location is causing us to misinterpret what we are measuring. The crisis this causes in cosmology is more profound than most people understand. The Hubble tension is more than just an uncomfortable difference between two measurements. It poses a major challenge to our knowledge of cosmic evolution. Cosmology is based on a framework known as lambda, cold, dark matter, or the Standard Model of cosmology. This model has been extremely successful in explaining observations from various sources. It explains how the temperature of the cosmic microwave background fluctuates, the abundance of light elements such as hydrogen and helium, galaxy formation, and the universe's large-scale structure. For decades, it has been the accepted model because it works so effectively in so many situations. However, the Hubble tension shows that this framework is incomplete or incorrect. When a model's predictions differ from observations at the 5 sigma level, scientists must take this seriously. The tension is significant because the expansion rate controls everything else in cosmic history. If the universe expands quicker, it will reach its present size in less time, making it younger. Current calculations based on the cosmic microwave background place the universe's age at 13.8 billion years. However, if the greater local measurement is accurate globally, the cosmos might just be 12.7 billion years old. That causes immediate concerns. We saw stars and glow clusters that appear to be 13 billion years old. Based on stellar evolution models, these stars would be older than the entire universe, which is also impossible. Our age measurements for stars are incorrect. Our understanding of stellar physics is incorrect, or the greater Hubble constant is not applicable to the early cosmos. Neither of these options is comfortable. The stress also influences our understanding of dark energy, the unexplained force driving cosmic expansion. Dark energy accounts for around 68% of the universe's total energy content, according to mainstream theories, but its qualities are sensitive to the expansion rate. If the expansion rate exceeds our expectations, dark energy's behavior may differ from current models. Some researchers stated that dark energy evolves throughout time rather than remaining constant, which would be groundbreaking for others.